Hi team, welcome to day 2 of SHIP Math Modeling Challenge. I heard from Lissa yesterday and she seemed to think that you guys had a good first session, that you had some fun and did some good work, and I hope that continues to be the case. There were a couple of issues, so Cassidy will make sure to get you access to everything, and then there was a small question on exercise 2A from yesterday. And so I will address that in just a moment. That was a kind of subtle thing within the problem, so I apologize for that, but it seemed like maybe that didn't hold you back too much. But today what we're going to do is look at a new method of solving linear programming problems. Yesterday you were doing what's called the graphical approach, where you either by hand, or I suppose you could have used a calculator or Desmos.com, that online graphing calculator, or some other program to graph the linear constraints in your problem, and based on that graph you can figure out what the feasible region is for potential solutions that will optimize your objective function. And we have this theorem that says that if an optimal solution exists for the linear program, it will occur at one or more corner points of the feasible region. So once you have the feasible region, you simply just test those vertices within your objective function to figure out which one optimizes it. And so that method is it's tried and true. It's a good way to start solving linear programs, but after a while, it has its limitations, and it's just a little tedious. So if the limitations aren't immediately obvious, I will clue you into those in just a minute. But for now, we're going to use Microsoft Excel, simply to expedite the whole process, right? So you can either just do it this way instead of by hand, or you can use this to check your work. And actually, that's what you'll be doing at the start of today to get practice with using Excel and the Solver add-in in order to check your work from yesterday. So that'll be good practice, and then you'll do some new stuff, which will maybe be more interesting, maybe not, I don't know. We'll see. Anyway, so the first example that we're going to look at today is the farmer example from Mr. T's second video that you watched, so the one that was specific to linear programming. And in that problem, we have this farmer who could choose to grow either corn or oats on his or her land. And so what I've done here, I've already set this up for you in an Excel spreadsheet. This has all of the variables defined, all of the constraints, the objective function, everything. So if you want to take a minute to pause this, you could go, if you haven't already, grab that Excel spreadsheet from the Google Drive, download it, open it. On the first, it's called the first worksheet, so at the bottom there's some tabs. The one that's called Farmer Example, if you highlight that, it'll show up with exactly this. And so you can follow along either now as I'm doing this, or if you want to watch everything that I do, pause, and then look through it yourself, that's fine. Everybody does things a little bit differently. Okay, so what I've done here is I've really just created a couple labels. So the first label just tells me that I'm talking about the farmer example, and then I've labeled my variable. So acres of corn I'm defining as X, acres of oats I'm defining as Y, and that's consistent with what Mr. T did. But then what I'm going to do is actually store the value associated with each variable in the cell below it. So in cell A3, I just initialized acres of corn to 0, and in B3, I initialized acres of oats to 0. And it doesn't really matter what you initialize them to, but I just always start with 0 because it's easy, and why make a guess when it's probably wrong? We know 0 is, well, almost surely definitely wrong when we're trying to max something, but that's okay. All right, so I've highlighted them just because this is where our solution will eventually show up, and at the end of the day I want to be able to just quickly look at this information and get the optimal solution, and so that's why those are yellow. And then for my objective function, I just wrote it out as a string of text on the left here and made it red to remind myself that that's the objective. So we know that the farmer wants to maximize his or her profit, and associated with each acre of corn, there was $40 of profit, so we took 40 times X, and then for every acre of oats, there was $30 of profit associated, so we added to 40X, 30Y, that'll give us the total profit. And again, I just reminded myself that I want to maximize that. But then the actual value of this objective function, depending on the values of X and Y, I'm going to store in cell B4. And in order to do that, what's nice about Excel is that you can reference stored values in other places on the sheet. And so then once those values change, all of the other calculations are automatically updated without you having to go in and essentially hard code those new numbers. So for instance, if I change X and Y right here, everything else is automatically going to update to those new values of X and Y, which is really, really useful. So in order for that to be accomplished, I tell Excel to reference those values, right? So for this 40X plus 30Y, in cell B4, I type in this equation. So I use the equal sign whenever I want Excel to actually calculate something that I'm typing in versus just put it as a string of text like it did over here. So I type in the equals 40 times whatever value of X I currently have stored. And so I tell it to look for X in cell A3. And then add to that 30 times whatever value I have stored for Y, which is in cell B3. So once I do that, it's going to have that current profit value within cell B4. And right now, since I'm not growing anything, I'm not profiting, so it's 0. All right, so then we have some constraints for this problem. The first two are what we call implicit constraints because they're not obviously stated in the problem. But we just know them to be true because of, I guess, reality, right? We can't have negative acres of either corn or oats. So we just make sure that X is non-negative and Y is non-negative. And again, I've just written these out as kind of a reminder of what those inequalities were. So when I code this into Excel, I first of all just want to reference whatever variable I'm talking about. So this time in cell B5, I'm only referencing the value of X, which again was stored in A3. So I type in equals A3. This is just a string of text to remind myself that I want it to be greater than or equal to the constant value of 0, which I've stored in D5. So D5 doesn't reference any other cell, right, because I always want X to be greater than or equal to 0, and so 0 is not going to change, so it's just coded in as 0. Same thing for Y greater than or equal to 0. I first reference where Y is, which in this case is cell B3. As a reminder, it's going to be greater than or equal to the constant value of 0. For the latter two constraints, those are explicit constraints because they were stated in the problem directly. First one says that the farmer only has 240 acres total to plant, so we can't plant any more than that, right? So however many acres of corn plus however many acres of oats cannot exceed that 240 value. So when I'm telling this to Excel, I first want to talk about everything involving the variables. So for us, that's going to be the value of X plus the value of Y. So here that's going to be the value in A3 plus the value in B3. As a reminder, this time it's less than or equal to the constant value of 240. And then this final constraint had to do with the number of labor hours that the farmer had available to him or her. So I think it was like to harvest corn, that took 2 labor hours per acre, and to harvest oats, it was only 1 labor hour per acre. So altogether, that can't exceed 320 labor hours just because of however many workers or helpers the farmer has. So when I'm coding that in, I first deal with the variables, which this time is twice the value of x, which is stored in A3, plus just 1 times the value of y, which is stored in B3. That's going to be less than or equal to the constant value of 320. All right, so once that is all set up and everything looks good, then we're ready to make the magic happen. And that's all accomplished through Excel's Solver add-in. So my add-in is already selected. So when I go to my Data tab, or depending on your version of Excel, you might have a Data menu at the top. Actually, I do too, but there's also a tab. So I go to Data. If I see the Solver option, then it's already added in for me. Hooray. If you don't see Solver, and if you're on a Windows machine, this will look a little different, but just look very carefully at all of your options. If you don't see anything that says Solver, then you'll have to physically add it in. So on a Mac, the way I do that is I go to Tools, and then all the way down to Add-ins, and I click it, and then so I get this dialog box that tells me I've only got Solver available to me. And so I just make sure this box is checked and then click OK. On a Windows machine, I'm pretty sure you have to go to, I think it's File, and then Options. And then there's, near the bottom of the dialog box, there's something about managing add-ins, and you click OK, and then I think there's the option to check the box for Solver. It's been a while since I've done this on Windows, but I think that was how it goes. So once you check that box and click OK, it should appear in your Data menu. But if you have any trouble with that, just do a quick Google search for Solver add-in Windows or Microsoft or whatever. Sorry, not Microsoft, but just PC or Windows or whatever. And you'll get step-by-step instructions. And if you know your version of Excel, that might be nice also to specify, but you'll probably be able to figure it out either way. All right, so once you have Solver loaded, then we're just going to go ahead and select it, and you get this box that pops up. And let me make sure not all of it fits in the screen, but all of the important stuff does. So I've already set this up for you. I think when you download it, it'll still maintain this. So we'll get practice at typing this in ourselves, but for now I just want you to see what it says and what it means. So first thing is it asks for the objective. So that's our objective function, or the value of the objective function, which for us is stored in cell B4, and it's highlighted. You see how the border of that cell is kind of dancing for us right now. These dollar signs, in case you're not familiar, it just tells Excel to fix a specific portion of the address for the cell. So anytime there's a dollar sign in front of something, that's saying, okay, hold that aspect fixed, right? So we're saying hold column B fixed and row 4 fixed. It's like, don't move. We definitely want this to be our objective function. Don't change that, no matter what. All right, so our objective is in B4. We know that we want to maximize it. Notice that it also gives us the option of minimizing, or if we haven't come across this yet, but if we need our objective to be equal to a specific value, then we can also specify that, which is nice. Next thing that we need to do is specify what values can change in order to optimize the objective function. So we want to indicate where the values of our variables are stored. So for us, that's in cells A3 and B3, right where it's highlighted. And this notation with the colon just indicates that you're selecting a range of cells. So this is saying all the way, so the entire range starting from A3 and going to B3. So for us, it's just the two cells that we care about. But that's the reason for the funny notation. Okay, and so then we tell it that there are some constraints, and the first one just says that the value of x, which was stored in B5, is greater than or equal to that constant value of 0, which you can't see right now, but maybe if you have the sheet downloaded, you can remind yourself that, oh yeah, we skipped a column here to remind ourselves that it's greater than or equal to the value that then is in D5. Same thing for the non-negativity of y. We do y greater than or equal to the constant value of 0, which was stored in D6. And then similarly for the two implicit constraints, we just reference the value associated with x plus y, which is in B7, that we wanted to be less than or equal to the constant value of 240, which was in D7. And then for the labor hours constraint, we needed the value of 2x plus y, which was in B8, to be less than or equal to the constant value of 320, which was stored in D8. So now we've got our objective, we're maximizing it, changing these variables subject to these constraints. This box I think is defaulted checked, and sometimes you want to be a little bit careful about this, but for our purposes in linear programming, it's fine just to leave this checked, because what that says is any variables that don't show up in a constraint, make those non-negative by default. We've specified that, which I think is a good practice to do, right? Because if you're going to do it by hand, or if for some reason this isn't checked one time, you want to make sure that that's accomplished. But for us, we'll just leave it checked because it shouldn't make any difference. And then the last thing and the final thing is to select a solving method. And so you want to make sure to choose simplex LP, so that's for linear program. If you don't have an option that specifically says simplex, you should have something that says linear. So whatever option says linear, choose that, because everything for our problem is linear, so it makes sense to use that kind of solving method. Alright, so once that's all set, we are ready to solve. So you guys can't see the button right now in the lower right corner, but there's one that says solve. So I'm going to hit it, and then my computer is going to think for a few seconds, and that's usually indicated by a spinning wheel, or your cursor is dancing around, or something in your icon bar is bouncing up and down. So just be patient. Computers aren't as fast as we like to think, but they're still a little faster than us sometimes. Eventually you get this dialog box that pops up that says Solver results. Solver found a solution! Yay! All constraints and optimality conditions are satisfied. Good to know. The default here is that it says keep solver solution. Just leave it as that, and then click OK. And then we're ready to look at the solution, which is nicely highlighted for us, that the farmer wants to grow 80 acres of corn and 160 acres of oats, which will give him or her a maximum profit of $8,000. And if you recall, that was the optimal solution that Mr. T found in his video yesterday. So that's excellent. That's how we use Excel with Solver to solve a linear program. Right, so this one I had already done for you. In the next example, we'll get practice actually typing in all of the different pieces and then running Solver one more time. And then in the third video, we'll actually do something a little bit new using this solving method. So I will see you all in just a couple minutes for that.